Good afternoon, everyone, and welcome to The Future of Energy, a monthly series presented by the Denver Museum of Nature and Science and the Institute for Science and Policy. I'm Trent Noss, Managing Editor at the Institute, and it's always great to see so many of you joining us from all over the country, all over Colorado. Thanks for taking some time out of your day to be with us. We're talking hydrogen today, which is a fascinating topic, incredible technology full of tantalizing potential for clean energy, and yet all kinds of challenges, question marks. We're going to get into it all today, implementation, R&D. We've received a lot of great questions already from the audience, and we encourage you to keep those coming as we go along. So our topic today is an interesting one because hydrogen is, on one hand, it's very simple. It's the simplest element and one of the most abundant in the universe. And so as an energy storage and transportation mechanism, it has incredible potential. There's a lot of ways that it can be used, but of course, not all of those are cost effective. The technology is catching up. It's going to require a lot of heavy lifting. So you've maybe heard about hydrogen fuel cells, which could certainly revolutionize transportation, reducing carbon emissions in that space. Maybe you've heard about hydrogen being used for manufacturing, other uses. There's a lot of potential avenues to go with this, and we're going to get into it with representatives from the National Renewable Energy Laboratory, which is right here in Colorado, and Xcel Energy. With my guests, who I'll introduce in just a moment. A couple housekeeping items before we get started. For those of you joining me on Zoom, feel free to use that chat feature to make sure that you get your questions in. We're going to have time for answering those toward the end. And if you'd like to catch up on our previous 2 episodes in the Future of Energy series, those are available on the Institute's YouTube page, which we can drop that link into the chat. We've covered electric vehicles and we've covered the grid. So without further ado, let me introduce today's guests, starting with Gray Byers. He is a program manager in the Business Innovation Group at Xcel Energy, and he focuses on a core team that is charged with delivering technology strategy and organizational framework to deliver on Xcel's commitment to be carbon-free by 2050. Gray comes from a background in electric distribution, engineering and management, strategic management, and a variety of innovation roles at Xcel. Gray, thanks for being with us today.
Thanks for having me.
Yeah. And we're also joined by Eric Payne. He's a senior licensing executive at the National Renewable Energy Laboratory, where he manages the commercialization of bioenergy technologies. Over his career, he has specialized in all matters relating to innovating, protecting, transferring, and commercializing technologies developed from research at universities and national labs. Prior to joining NREL in 2009, Eric served as technology manager at the University of Illinois, where he focused on licensing biopharmaceutical, engineering, agriculture, and energy innovations. And he has degrees in genetics and microbiology from Purdue University. He's also registered to practice before the U.S. Patent and Trademark Office as a patent agent. Eric, thank you for being here.
Thanks so much for the opportunity, Trent.
Sure. So we're going to start with Eric. He's got a few slides to share with us. So take it away, Eric.
Great. Well, thanks so much. Really appreciate the opportunity to talk to you all this evening. Always we'll jump at an opportunity to talk about hydrogen energy in the future. So yeah, as Trent mentioned, my name is Eric Payne. I'm a licensing executive. I work in the tech transfer office of NREL. So while I'm certainly no expert in hydrogen, I work around a lot of experts, and I manage part of the portfolio that's focused on commercializing hydrogen fuel cell technologies. And we have a big initiative at the laboratory called Electrons to Molecules, part of which is focused on finding renewable paths to producing green sources of hydrogen. So yeah, it's a pleasure talking to you today. So let's go to slide number 2. So I really thought I'd start off by with an introduction as to what hydrogen is. It really is the most abundant chemical in the universe. 75% of the elemental mass of the universe is hydrogen. It's the most simplest of elements. It's one simple proton. It's the only element that exists without a neutron. And so you can see it here graphically represented. On the picture to the right is water, so H2O, 2 protons and 1 oxygen. And this reaction really starts to show you what we can do by splitting water electrocatalytically into its respective components of hydrogen and oxygen. And then if you run that reaction in reverse, you get water and electricity. So that'll sort of form the basis of the rest of the presentation. But a long history here. We've got first recognized by Henry Cavendish. He gave it the term, the Greek hydro, which is water, and gen, creator. And at room temperature, it's colorless, odorless, it's non-toxic, and it's a combustible diatomic gas. It tends to disperse really quickly in air. And so it seems like we got a few questions in advance about safety, and I'll go into that in a little bit more detail. And I like this as a biologist. You know, life wouldn't be possible without hydrogen. It really does make possible these acid-base reactions, which is the fundamental basis for biochemistry. So next slide, please. So in order to talk about energy, hydrogen energy, we need to talk a little bit about the mechanics of the storage and the form that it comes in. And so I thought I'd really quickly just touch base on the density, because at room temperature, hydrogen is a gas. And really is only 1/300th the energy density of gasoline at room temperature. So you really have to compress it in order to make it energy dense enough to transport it and then utilize it. So 1 kilogram of hydrogen, just to put that into perspective, 1 kilogram is about the same weight of a 1 liter bottle of water, is about the same energy as a gallon of gasoline. And that assumes that you really compress the hydrogen gas into a form that's utilizable. The beauty of hydrogen is that it can be easily produced from water. Again, H2O, it's two measures of hydrogen to 1 of oxygen, or it can also be produced from natural gas. And as a matter of fact, about 95% of hydrogen that we use for industrial purposes today are actually sourced from natural gas in a reaction that I'll talk a little bit more about called steam methane reforming. And then it can be converted into electricity through a fuel cell, and we'll talk about that reaction. The energy to produce hydrogen through what I call electrolysis, through the splitting of water, can be sourced from renewable resources, from wind, solar, nuclear, and biomass. And it can also be done via traditional sources, and that's a majority of how we drive that electrocatalytic reaction today. Hydrogen is flexible in the sense that it can be combined with CO2 to produce other organic carriers like methane or formic acid. And I'll talk a little bit more about the promise and some of the R&D that we're doing with formic acid in a future slide. So next slide, please. Yeah, so some of the technological challenges related to hydrogen storage are at room temperature. Hydrogen is actually somewhat not very energy dense. And so at room temperature, hydrogen gas has about a fraction really of the energy density of gasoline. So we have to really put it into a different form for hydrogen to be useful. And so compression, that is compressing hydrogen into another form, it can be somewhat energy intensive. So to get it to 10,000 PSI still yields about 1/4 of the energy of the volume of gasoline. And so it can require at certain temperatures large storage tanks. And this is a big research priority for the national labs and for the US Department of Energy, is to find ways to really concentrate the density of hydrogen into a form that's utilizable in fuel cells and in power plants. The good news is there's a lot of facile ways that you can convert the energy of hydrogen into another carrier. And so I list 2 here: natural gas, CH4, 1 element of carbon with 4 protons, 4 of hydrogen. And so you can actually combine hydrogen into CO2, getting a reaction, an intermediate reaction of carbon monoxide, thereby going to methane. And then you can run that reaction in reverse through steam methane reforming to retrieve those protons, that hydrogen from natural gas. You can also take it to ammonia, and there's a lot of existing infrastructure for using ammonia, for example, using nitrogenous fertilizers. And that is a catalytic separation that is well known in the literature. And then liquid hydrogen certainly does require quite a bit of energy to get it down to negative 253 C. But it can be certainly done very quickly, and it can be transported via existing methods of transportation to utilize at a fueling station, or it can be generated and compressed on site. And there's a lot of attention being paid to that. I mentioned very briefly the liquid organic hydrogen carriers, so toluene. This was actually a molecule that was investigated quite some time ago for use in fuel cells to strip those protons off. And then formic acid, which is actually a liquid at room temperature. It's pretty safe. It's a food additive. And so formic acid is CH2O2. And so two of those protons can be stripped off very easily. And then we're actually investigating solid state traps. And so sodium borohydride is borax soap, believe it or not. That is a very good energy carrier for hydrogen. And so it's relatively easy to strip those protons off. And then just in terms of mixing into existing pipelines, so NREL's done some studies that at least 15 or 5 to 15% of hydrogen can be mixed into existing natural gas pipelines as a means of leveraging existing infrastructure to move hydrogen throughout the country with really no modifications. And so we sort of view hydrogen gas as infrastructure compatible. Next slide. So I really like this slide in terms of graphically representing everything that we can do with hydrogen and how we can generate hydrogen. So this really does demonstrate the myriad ways hydrogen can be generated here on the left, from nuclear, from fossil existing resources. And a lot of attention is being paid on renewables. And that's a lot of the work that we do at the National Renewable Energy Lab, specifically electrocatalytic separation of water splitting from renewable energy sources like wind and solar to make hydrogen gas. And then hydrogen can be generated from existing and renewable resources, and that can be used to smooth the gaps between generation and usage. And a lot of people don't know this, but the right-hand side of the slide represents all the ways that we currently use hydrogen. Fuel cell vehicles is a relatively small part of the vehicle fleet, but every gallon of gasoline is made through hydrogenation using hydrogen. It's used in ammonia fertilizers, and so that's a reaction called Haber-Bosch, and metal refining, all kinds of industrial processes really do require hydrogen. So going forward, it's going to be important for us to find renewable and sustainable ways to generate hydrogen. Next slide. So how does this work? How do we actually generate hydrogen from water? This is the water splitting reaction. So really, you have a cathode and an anode. You run electricity through those systems and you separate water. You separate the gases, the constitutive components of water, into hydrogen gas and oxygen. And at that point, you can then separate, purify, and compress those gases to be used later on. And so going on to the next slide. Here, I just represent a fuel cell vehicle, and how this can be used to power a vehicle is effectively taking oxygen from the air, combining that with hydrogen, which is stored in a tank on the vehicle. You run that through a fuel cell, and really the only byproducts are electricity to fuel the battery that generates your power to motivate the car, and water. That's the only byproduct. So it's really the cleanest source of fuel known to us. And so that's really the promise of fuel cell vehicles. And so if we go on to the next slide, it was hard for me to limit this to just this list of fuel cell vehicles, because these are really cool cars. We have some of them at the laboratory where we are testing them. But the Hyundai Nexo, the Mercedes, Nissan, Honda, Toyota, it really does seem like all the auto manufacturers are seeing hydrogen as a future way to power our cars. And just to give you some perspective on the range, the Hyundai Nexo has almost a 400-mile range. The Clarity 360 and the 2021 model of the Mirai will have a 400-mile range. And so these vehicles consume hydrogen at a rate of about 2.8 pounds of hydrogen for 100 miles, which is pretty staggering in terms of energy density, and a lot of promise there. And most notably, we're certainly reducing the amount of time for refueling. This is a lot of what we do at the laboratory and throughout the DOE complex, really to get the fueling of these vehicles at around the same time that it would take to refuel your gasoline-powered car. Next slide, please. So a few of the challenges, as can be appreciated, whenever you have to compress hydrogen to these pressures and the temperatures, it does require a lot of energy. There is a huge endeavor to create new pipeline infrastructure for moving hydrogen. So a lot of attention is being paid to generating hydrogen at the point of use, and in particular using excess electrons through renewable resources. And then we certainly need an additional level of R&D to produce hydrogen and be able to distribute it safely. And then also refueling is a lot of the challenge right now for vehicles, but the great news is we're developing a lot of innovations to really address that. And with that, I think I've got one more slide. I just thought I would touch very briefly on a project that we have at NREL. Our corporate partners at like Xcel and SoCalGas are really important to us, bridging the gap between bench scale inventions and the market. And so this is an example of the kinds of research that we're doing at NREL. And so here you can see we're taking renewable electrons from solar and wind. This might be stranded resources, excess renewable electrons that we don't have a use for at some times of the day. We then electrocatalytically reduce or water split the water into hydrogen and oxygen. And you can store a portion of that onto the existing pipeline. But as a microbiologist, what I get really excited about is these strains of RK bacteria. They are methanotrophic that can be fed hydrogen and CO2 and make natural gas, which is a renewable resource, and that's fed onto existing pipelines. And so a lot of promise in terms of what we can do to leverage renewable resources to produce a hydrogen carrier like methane and pump that into the existing pipeline for use. So with that, I'll hand it over to Gray, but certainly happy to take any questions at the end.
Terrific. Thank you, Eric, for that primer. That was excellent. So yes, let's bring Gray into the conversation, and Gray is going to tell us about some of the applied integrations that Xcel is working on.
All right. Thank you, Eric and Trent. Again, my name is Gray Byers. I'm in the Business Innovation Group here at Xcel Energy. I'm based in Denver, which is, I think, where most of you guys are coming from what I saw. So probably most are familiar with Xcel in general, but just kind of the obligatory level setting here. So we're serving eight states, Colorado obviously being one of them, 3.6 million electric customers. So a lot of load. We have commitments to wind energy is kind of our main renewable asset at the time, being amongst other categories that we're nationally recognized in, and pride ourselves on being innovative, which will kind of bring me into my next here, which is our carbon reduction goals. So for those of you who don't or haven't heard, hopefully everybody's heard, we made a pretty strong commitment to kind of a two-tiered, I guess, goal for our carbon reduction. And this is based off of our carbon generation from 2005. So in 2030, we're looking to reduce that to 80%, or by 80%, I should say, and then be 100% carbon free by 2050. So as you can imagine, with that becomes a lot of implications, both strategically and just sort of how we approach that. So one of our efforts internally is creating a very large cross-functional team within Xcel that's charged with how do we organize technologies that we want to go after, how do we intake them effectively, and how do we make prioritization into our overarching strategy of how we decide what technologies are appropriate, both technically for the environment and for our customers ultimately to reach these goals. So within those categories, we've broken them out into major ones, hydrogen being one of them. So today focusing on kind of the implications of hydrogen and our general approach within that overall framework of our carbon reduction goals. So talking about hydrogen, to kind of piggyback on some of the stuff that Eric was talking about. So from our perspective, like Eric mentioned, most hydrogen today, if not all, or overwhelmingly, it's done by steam methane reforming. So that's a process that Eric talked about, but it is carbon emitting. So hydrogen produces great qualities in terms of an energy carrier and has great potential, but not to reduce carbon unless it transitions into efficient ways to create it from either carbonless or carbon reduced generation sources. And so for us, that would be, renewable sources that we can create hydrogen directly from through electrolysis or nuclear. And there's also coal, which can be done with sequestration, which is what we would call blue hydrogen, where it's still emitting carbon, but it's sequestered. So it could be more considered a transitional fuel, a transitional means, I should say. And so kind of the off takers is a big question. Okay, we have hydrogen. What exactly do we do with it? What does that mean? So from our perspective here, kind of on the left, I've put what our major kind of approach or what we're kind of looking at, I should better say. So hydrogen blending seems to have great promise with natural gas as sort of a transitional way to reduce the profile of combustion turbines. So you can actually blend hydrogen with natural gas and reduce carbon output of existing turbines. And so that's good for the utility because obviously we already operate those, we know how they function, and there's only slight modifications, if no modifications needed on newer assets for doing that blending. Also, alternatively, you can blend hydrogen for direct use in the natural gas system. That has obviously implications of material types, and there's only certain thresholds you can blend to. So it does have limitations, but something we're looking at. Also ammonia. So as Eric mentioned, in terms of carriers, ammonia is a somewhat paradoxically, at least logically, ammonia has actually more hydrogen density than hydrogen itself for the same container. So it's very well understood given the agriculture markets for fertilizers of how the handling and things like that. So we're looking at ammonia used for combustion directly within turbines as well as long-term storage. So a huge issue within the carbon-free journey is something called seasonal storage, which is basically taking seasonality issues within renewables and offsetting them to different time periods within seasons. So you might think of solar, it's sunny in the day, we need more power at night. That's sort of a inter-day shift, whereas a seasonal shift would be wind blows a lot in the winter, but we need it spring to summer type of thing. So long-term storage is a huge problem to solve, and hydrogen and hydrogen carriers have pretty profound implications within that. And then, like I said, renewables to green hydrogen is kind of where we want to go. So green hydrogen being no carbon footprint into the fuel. And then sort of what do you do with that? Like I mentioned, creating a fuel itself, creating storage, or participating in secondary markets. So chemical processes and industrial processes are heavy on hydrogen. So just some of the kind of potentials out there for what we can do with it. So the good news is hydrogen, I think, from the US's perspective, it's been relatively quiet globally, particularly in Asia and more so in Europe here recently. There's been a lot of interest in hydrogen. As you can see just from July, this is mostly just trying to illustrate more than actually convey the information. But the point is that a lot of projects are starting to take hold and to
Oh, Gray, I'm going to jump in just for a second. Sorry, I think your mic is coming in and out. Could you just say the last bit again?
Yeah. Did it cut out when I moved to this slide here?
Yeah, let's start there.
Can you hear me good now?
Yeah.
Okay. Sorry about that.
No problem.
So yeah, this slide is really not for you to consume the information, just to illustrate the sort of that. Although worldwide hydrogen has been gaining traction, the US has been kind of lagging a little bit. And so here, just in the last since July, you can see multiple projects that demonstrate different portions of the value chain and different applications to either trial and pilot or trial at scale. And so that's really promising because there's a lot of work to be done to sort of prove out, how the hydrogen economy would work and all the supply chain and foundational and off-taking elements within that. And then here on the right, I have, Xcel's gotten into the mix, which I'll talk a little bit here, where we've been partnering with the Idaho National Lab to demonstrate a pilot approach to hydrogen production in conjunction with all these other projects to try and reach hydrogen at scale. And so a lot of hydrogen approach to creation is renewables are intermittent, which basically means that they're, coming off and coming on. And there's some times when you don't need your renewables, right? So in that circumstance, you would do something called curtailment, where basically if the wind's blowing really hard overnight and you don't have anybody to use it, you have to curtail or not use that energy. And so traditionally, or a good approach would be, all right, well, let's store that otherwise curtailed energy or use it to make hydrogen. But we have kind of a unique scenario where a nuclear plant is designed to run at top performance or top output at all times to run most efficiently. And with the nature of renewables, we're actually having to back off the nuclear plants and consume those renewables over the nuclear plant, which is very inefficient. And so this concept is actually, instead of backing off the nuclear plant, actually using the nuclear plant to create hydrogen during those peak times of renewables. So it's kind of the opposite thing, but accomplishing the same goal and still producing carbon-free hydrogen through nuclear. And so with that, some of the kind of a little bit of nuance here that I wanted to go in technology-wise is traditionally low temperature electrolysis is kind of what's taking hold, specifically to what Eric talked about with the PEM electrolyzers. We are going to try something called high temperature electrolysis. And so this is done with solid oxide electrolysis cells. And so basically those, you can see the chemistry on the right, but I won't go too much into that. But those are basically created into stacks, which are what is making the system that is the high temperature steam electrolysis. And so this is not as advanced technology as the other ones. But the key is that since we're in a nuclear plant, we can take waste steam and heat up the stack. We can get up to 30% more efficiency in the electrolysis process. So you can basically use 30% less electricity to perform the splitting of the water by having that high temperature steam coming in and basically priming the system. And so Idaho National Lab, like I said, is creating and testing this open source stack. And we are going to pilot the system up to about 1 megawatt, which is about 90 kilograms a day of hydrogen. And so the intent of this hydrogen pilot is pretty much to complete technical and economic assessments, which is basically in the region, what do we actually have for offtake opportunities and creation opportunities in the hydrogen environment, demonstrate the connections at the nuclear plant, and then validate that system that I was talking about just before that's coming out of Idaho National Lab. And so we have a consortium of Idaho National Laboratory, ourselves, Arizona Public Service, and then Energy Harbor that are all participating in this to create this system. And then from there, we're obviously going to demonstrate the production of hydrogen, which is the point of this. And then the next steps will be to kind of determine path forward on scale and uses on an ongoing basis. Okay, so and this is my last slide here. So just kind of to talk about the outlook, I guess, of the hydrogen market in general and sort of where we see, where is this going and where could it go? I think there's certainly constraints. So capital cost being a key consideration, price point has to reach parity with other systems today in order to be accepted by regulators and also prudent for us as an operator. So electrolyzer costs need to come down significantly to reach parity with steam methane reformation. We think that's about $250 a kilowatt hour. And so that being a pretty key component, as well as the capital cost for transportation and storage. Obviously, there's a lot of infrastructure challenges to be able to move hydrogen around or store it effectively, which is outside of our core business. And kind of within that, I'll skip this next one, but we're really set up to move electrons. So it's kind of limited to create on site. So you kind of have to make a decision of transporting electrons or building infrastructure to move hydrogen. And then just cost of commodities like natural gas and the steam methane reforming process is certainly a huge factor. And that fluctuation in natural gas prices will be key in whether the cost to do electrolysis will reach it. And then I think the opportunities here. So Eric talked about this, but hydrogen carriers, huge opportunity in terms of making the cost of transport and storage cheaper and be able to leverage existing infrastructure. Seems to be, where it needs to go. And it's kind of challenging because where do you pick a point of, do we start building out hydrogen infrastructure or some other carrier? And then reversible fuel cells, that's basically a two-way system. So it can perform the electrolysis and also create the electricity. So from a long-term storage, that has implications within the efficiency of those systems. And then policy is always going to be a factor, incentivizing proliferation, just like was done in solar and wind environments that help them to become mature technologies. And then carbon tax, which we're not necessarily stating any sort of position on, but it's worth noting that a carbon tax would change the economics of the hydrogen market and helping it to reach what would be economical compared to natural gas. And I think the biggest thing is just how do we reach economies of scale that are actually going to drive these prices down? We can't just assume that it's just going to take off and that all these price points will be reached. You need users. And so vehicle adoption seems, particularly heavy transport seems, heavy freight and things like that seem like the likely first adoption to really create an actual consolidated economy of production all the way to off-taker, which can start to actually reach the scale and drive some of these costs down, which would then allow it to proliferate in other aspects of the hydrogen economy and actually reach the H2 at scale diagram from NREL that Eric showed earlier. And that's all I have. So I'll stop there, and like Eric, willing to answer any questions you guys may have.
Well, thanks, Gray. Really appreciate that. Look, lots of fascinating pilots going on there, and we are getting a ton of great questions from the audience. So I'm going to start to work through some of these rapid fire in the time that we have left. I wanted to start with the water itself. We had a couple questions come in about how do we source the water that's being used for electrolysis? Can we go to the ocean and get a bucket full? Are we using local fresh water? There was a little concern about that. So maybe Eric, if you could speak to that first, and then Gray, add on if you'd like.
Sure. The answer is yes. There are a few technical challenges with sourcing, doing the electrochemical splitting of water with brine, with seawater, but it definitely is possible. And in particular, as Gray alluded to, if you can pair that with an excess heat source or electricity source, you can do the distillation of seawater into pure water. And at that point, you can go directly into drive the reaction from water to oxygen and hydrogen. A lot of research being done on the electrocatalytic systems to do that. Right now, they're pretty robust in terms of their operation, but they certainly could be better. And I think that's a big part of the capital cost that Gray alluded to.
Yeah, I actually went back and forth of adding water to my constraints. It's definitely an issue, I would say. I mean, I think, within the context of production on site, particularly in a nuclear plant or other plants, water rights are secured. So it's kind of within that. And the volumes we're talking about are fairly small, but hydrogen at scale would have water implications for sure. And so I think that is a very valid discussion. I mean, we've kind of gone through at a high level, I would say, of just inventorying implications of existing water rights, future consumption water consumption technologies. But that's still a story to play out for sure. So I think it's a very valid question and something that's definitely of interest to try and understand what that would look like at scale.
Yeah.
Actually, regionally, there's a lot of issues, I guess, depending on where you are.
Yeah, absolutely. Well, and that brings us to potentially another constraint, the safety of hydrogen infrastructure and building out any new fuel, relatively new technology. Can you both speak to some of the safety parameters around hydrogen?
Yeah, maybe I can get us started, and Gray can add to this as well. So from my perspective, hydrogen is, with any energy source, there's going to be implicit dangers and require safe handling. But a lot of that safety is built into the design and how we move fuels around. So in particular, right now with gasoline, that is sort of built into the production, storage, and transportation of how we use the fuel. And I think the same is true for hydrogen. Hydrogen has some benefits going for it. The first is it's non-toxic, and as a gas, it immediately and quickly dissipates in air, rendering it non-flammable above a certain concentration. So, but a lot of the storage tanks, a lot of the storage capacity, and the way that we refuel, there's a lot of attention being paid. The same way that we've designed gasoline fueling stations is really being built into the design of how we operate those systems. So I think there's a lot of promise, and certainly a lot of research has gone into ensuring that those systems are safe, including a lot of vehicle studies where we actually take these vehicles and we puncture the gas tanks and we see hydrogen. Actually, it's pretty cool to see. It just kind of, there's a quick energy release and then it dissipates. All in all, I think we've taken a very careful look at the safety of hydrogen for fuel cells and for vehicles in particular.
I think that well covers it. I mean, the vehicles themselves are certainly not my area of expertise, but I mean, the reality is, hydrogen is in use today. I mean, there's pretty well understood, pipelines and storage, and there is a lot of knowns, I guess, around that. So I mean, I think that the precedent is there to do it safely, and just to Eric's point, any fuel has its risks, and some of the other carriers less so. But I think the industry is well positioned to replicate some of the existing measures already taken to be able to safely execute on any hydrogen storage or transportation.
And just one thing that I liked what Gray alluded to earlier is he mentioned other carriers for hydrogen, and I think there's a lot of promise to that. And so formic acid, I saw that it was in the chat section, and that's a great molecule. It's a liquid at room temperature. It can be transported like a liquid. And then at the point of use, the hydrogen can be stripped from formic acid. It's CH2O2. So a lot of promise in metal hydrides and other ways that we can store hydrogen that make it very safe.
Great. Well, and that brings us to another natural question, which is about how much of our existing infrastructure. Gray mentioned in his presentation that Xcel is currently set up to move electrons, not hydrogen. So in terms of as we move toward potentially implementing this technology on a wider scale, how much of our existing infrastructure can be retrofitted, and how much has to be created from whole cloth? Gray, do you want to start on that one?
Yeah, sure. I kind of alluded to it in the presentation. So there's certain thresholds, and the for those that don't know, the concern is something called embrittlement. Hydrogen embrittlement basically causes certain metal types to degrade and crumble, essentially. So there's a lot of studies going on. NREL, in fact, has done one of them, that basically the thresholds of existing systems that can handle certain percentages, usually up to about 15%, but some areas of the world are more, as far as how much hydrogen you can have before you reach some of those material concerns. So, but then sort of larger than that, in 100% hydrogen environment, I think there's a lot of consideration of, there's obviously existing pipelines, existing transportation methodologies for certain types of carriers, but again, to the point, it's, the commitment of what type of infrastructure, and can we move the electricity and then produce on site, or do we actually get into physical transport of the fuel itself? And I think that's still an economic question that remains to be answered.
Eric, question for you about the fuel cell vehicle market. You showed that the major manufacturers are starting to get on board with these models. Is the fueling infrastructure there right now? Are folks just kind of, they're sort of on their own as to how do they fuel up? Could you speak to that question a little bit?
Yeah, it's a totally fair question, and certainly something that you'd have to research before investing in that kind of vehicle. It's getting better. NREL maintains an alternative fuel data center where you can actually look up online where you can access hydrogen. Believe it or not, I think we actually produce hydrogen up at our Flatirons, what used to be called the National Wind Technology Center. And so it's getting better, but just like electric vehicles, where charging stations a decade ago were really hard to find, they're now pretty accessible. So I think we're investing in those, and it's getting a lot better. And in particular, I think something that Gray said that I really resonated with me. In contrast to the production of gasoline, which is really centralized and then transported out from sort of a hub and node model, the beauty of hydrogen is you can produce it relatively easily at the point of use. And I think that's what we're going to have to maybe start looking at more and more and getting comfortable with, is that you would actually produce hydrogen closer to a fueling station. And those are easy technologies. Again, water splitting, it certainly does present some water issues and some other issues, but producing hydrogen closer to the point of consumption would be something that would make the fueling station a little bit easier to manage.
Yeah, and you beautifully anticipated a question I saw John just put in the chat, which is just, do you anticipate that perhaps as more hydrogen comes online, that we would see a trend like we have in the grid away from centralization and more hydrogen produced by end users in that regard? That's probably a little ways out, but if you'd like to put on your prognostication cap.
Yeah, I think it's a big part of where we view the landscape going is number one. Oh, sorry, go ahead. Yep. Yeah,
Oh,
great.
ahead.
I think you're much better positioned to take this one.
Go ahead, Gray. Why don't you take that one?
Okay. Yeah, I think we would agree. I mean, it makes sense as the technologies come down, is really how accessible is that technology at the point of use, I think, because I mean, the dynamics of the grid is the surplus electricity or the use of renewables can really anywhere, right? So it doesn't necessarily have to be at the point of where the renewable or where the extra production is. So you kind of delocalize all that consumption as hydrogen producers, wherever the point of use is. It's just a matter of, do the small scale economics of producing it at that site turn to where it actually can be competitive, subsidies or otherwise, with diesel fuel or traditional fuel or electric vehicles.
Question from Davi on permitting. What is the permitting process like for hydrogen production facilities? Is it on par with other energy sources, or are there quirks to it? That one might be for Gray.
Yeah, I got to be honest. That's certainly not my area of expertise in terms of what I mean. I know it's new. I mean, I imagine the permitting is probably unique in our pilot scenario because it's all contained on our site. So it's more sort of approval of, design and things like that. And that we're, doing things that are prudent within our grant and within our regulators. So I honestly cannot speak heavily towards any permitting implications for us specifically.
Fair enough. Well, we are getting very close on our time, and I wanted to make sure that we get you out of here on a note of optimism and excitement. So I'm curious to ask each of you, what is an element of hydrogen research or implementation that you are really excited about over the next few years, something that you just think is super cool and want to share with our audience? Maybe we'll do Eric first, and then Gray can have the last word.
Yeah, so definitely I'm biased. I get really excited about the promise and the flexibility of hydrogen fuels, but the potential, I think, to split water and also split CO2 and have those two molecules combined, because you can run those reactions in parallel, right? You can use electricity from existing or renewable resources to split water into hydrogen and oxygen. And if you look at CO2, it's pretty much the same thing. Obviously, very different from an atomic perspective, but electricity can be used to split CO2 into an intermediate compound, carbon monoxide, and then that can be hydrogenated to natural gas. Again, hydrogen sort of underpins all of most industrial chemistries, and the potential of combining renewables to producing hydrogen to get to that carrier, which I think is really exciting because it's infrastructure compatible. Gray, Xcel has a hard enough job the way it is, and for us to design molecules that can fit into existing pipelines is really exciting to me.
Yeah, thanks, Eric. I would kind of agree on the same line of just the dynamicy of hydrogen being interesting. I mean, hydrogen's been of conversation for quite a while, and it's kind of been one of those things that felt a little bit like, when's its day going to come? It feels, obvious, but not ever present. And it feels like we're on that cusp finally. And I think for me, the combustion technology, as well as the long-term storage, I mean, to think that traditional, combined cycle units that, utilities are really used to operating can get to 100% hydrogen combustion. That's a totally clean, no carbon fuel with really minimal expertise change. I mean, I came into this, story of, wow, getting carbon free when I first started digging in, getting carbon free by 2050 is going to be extremely hard. And I would say within the last 2 years of working on this, it's very promising and very possible. And that excites me that, hydrogen has a very real possibility and likely possibility to play a massive role in maybe beating those targets of getting our reduced carbon and really making all our lives better. So I think that's exciting.
Yeah, absolutely. Well, I wanted to thank you both for your time and expertise today. This has been an outstanding conversation, and I know I learned a lot. I hope our audience did as well. Certainly wanted to thank you and your organizations, National Renewable Energy Lab and Xcel, for all the work that you're doing in this space. So thank you, and hopefully maybe we can have this conversation again in the future and talk about even more hydrogen development. So thank you both. And thank you to our audience for tuning in today. We hope you enjoyed it, and look for another Future of Energy session next month. We'll be back on Tuesday, December 15th. And thank you to all my colleagues at the Institute and the museum who make this series possible. We'll look forward to seeing you next time.